In this module we will discuss wave reflection from a perfect conducting medium when the wave is incident normally onto the surface of the perfect conductor. So far we have assumed that there is only one kind of wave propagating, which was the positive z going wave. We said that mathematically there can be situation or there can be a expression in which the electric field would also propagate or the wave would also propagate along minus z direction, right? But we did not elaborate how one can produce a minus z propagating wave unless there is a source of a wave which would propagate the waves along minus z direction. One way of getting this negative propagating wave is to actually make the wave reflect off a surface. Okay, so accordingly consider this surface that I have. Okay, assume that this entire surface or this entire region is a perfect conductor. We will not worry about what happens inside this region and how the effect of imperfect conductivity would come into effect. Here we will assume that the medium is perfectly conducting, therefore its sigma is going off to infinity. Okay, and this is of course the direction of the wave propagation along the z direction, and I have kept this particular conducting surface, a rather thick conducting surface, at z is equal to 0. We can also mark off one of the axes as x axis, right. So the conducting surface, if you imagine like this, then this would be the direction of the wave propagation, right. Okay, according to this direction the wave is propagating, and this my finger would point along the x axis and this thumb would point along the y axis, forming up a plane which is kept at z is equal to 0, and to the right of this plane is all a conducting medium, and to the left of this plane we can assume it to be a dielectric, a perfect dielectric or free space. Okay, so the wave would actually propagate, you know, starting from some very far away case. This is a plane wave which is coming in here and it would hit the conductor, and what would one expect to happen? Can you just have a situation where the wave would propagate and there is nothing that is happening onto the left hand side? A moment's reflection should tell you that this cannot be the situation, because for this situation to occur there has to be electric fields inside a conductor. We have shown in previous modules, you know, like when we discussed electrostatics, although we discussed the case for electrostatics, it is true that you cannot have electric fields, whether it is static or dynamic, inside that of a conductor. So what really happens is that there won't be any wave inside the conductor, but rather the entire wave must fall back or must be reflected off the conducting surface. Okay, so the wave would come in, right. The electric field vectors are all directed along the x axis. The electric field vectors would come in here and then they would get generated with electric field vectors along this particular direction. That is, they would be reflected electric fields that are set up or reflected wave that is set up. Accordingly, since we have two different kinds of waves, we can call this wave as incident wave, okay, the wave which is incident from a faraway source and reaching the conductor, and this wave as reflected wave, right. At this boundary, you know, very close to boundary, I have two electric fields sitting here, and the sum of these two electric fields, because they are tangential to this surface, remember these are tangential to the surface, and we know that from the boundary condition the tangential electric field must be equal to 0. You will have, since the tangential electric field must be equal to 0 at the boundary z is equal to 0, we will have E incident amplitude plus E reflected must be equal to 0. This is the amplitude of the incident and amplitude of the reflected field. Together they must add up to 0 because there is no tangential component of the electric field. Of course, at any other region of space that you consider, this would actually be the total field in the region 1, right. Total E field in region 1 will be sum of incident field with an amplitude, let us say E0I e to the power minus jkz plus amplitude of the reflected fields, okay, at e power and going as e power jkz, right. Why should this be e power jkz? Because this is the wave which is propagating along minus z direction, whereas this incident wave is propagating along plus z direction. So this would be the total electric field at any z in the region. So for example, at this point of z, this would be the electric field. At the boundary at z is equal to 0, the sum of the electric field vectors must be equal to 0, because this entire electric field is along x axis, and the field component which is along x axis onto the surface of the conductor means that this would be tangential, and therefore at the boundary at z is equal to 0, that you substitute for z is equal to 0 in this expression, what you find is that EOI plus EOR, the amplitudes must be equal to 0, from which it is very clear that EOR must be equal to minus EOI. So clearly the amplitude of the reflected wave is minus amplitude of the incident wave. Okay, if the incident wave can be written as the x polarized but z propagating wave, and write this as e power minus jkz, the reflected wave, right, can be written as minus x hat E0i. Remember, E0i is equal to E0r, or rather minus E0i is equal to E0r, e to the power jkz. So you can see that the reflected field would be directed along minus x direction, having the same amplitude E0i. So you have an equal amplitude wave, but another wave which is 180 degree opposite to this one. So clearly in the region before the conductor, that is in the region in front of the conductor, you will actually have an interference of the waves created, right. So you have one wave which is propagating in this way, there is another wave which is propagating in the backward direction. These two waves are at 180 degree phase difference with each other, therefore they will interfere and then form what is called as a standing wave pattern. Okay, so they form what is called as standing waves or standing wave pattern. Okay, so this is what would happen in front of the conductor. So you can actually see that the standing waves are formed by writing down the expression for the electric field, right. Electric field in region 1 is given by x hat E0i is a common factor, I will take this out, e power minus jkz minus e power jkz, and utilizing the relationship for sine and exponential of jkz quantities, you can actually see that e to the power jkz minus e power minus jkz is actually 2j sine kz, right, and there is a minus sign here, so therefore this becomes minus 2j x hat E0i, right, sine kz. You might say, where is the standing wave happening? Well, this is just the phasor that we have written down, right. So this is the phasor component of the electric field, but if you write down the full electric field E, right, that would be obtained by multiplying this by e to the power j omega t and then taking the real part. So when you multiply this expression e power minus 2j x hat E0 EOI sine kz with e power j omega t, which is actually cos omega t plus j sine omega t, and then take the real part, you will see that cos omega t 2j term will be imaginary, therefore that will not be present, and j and minus j will be plus, and then the electric field vector that you are going to obtain will be 2 along x axis, of course this would be 2 E0i sine kz sine omega t. This is clearly not a propagating wave, right, this is clearly not a propagating wave, this is in fact a standing wave, right. A propagating wave is characterized by some function of omega t minus kz, okay, whereas a standing wave is characterized by some function of omega t and some function of z. In this particular case, this is a standing wave. Okay, what is the amplitude of the standing wave? The standing wave amplitude is 2 times E0i. Does it make sense? Yes, because this is simply addition of 2 out of phase waves, right. So when you look at that one, the maximum amplitude can go up to 2 E0i, right, and that is, there is no surprise out there, and this is the expression for the electric field. What about the expression for the magnetic field? To obtain the expression for the magnetic field, let us actually write down the corresponding components of the magnetic field. We know that electric field is along x direction, right, the magnetic field must be along y direction. So your magnetic field component, let us first write down the phasor form, that would be easier for us to write that for this particular case. So the magnetic field in region 1 will have two components. One component is the incident component, which would be associated by writing this amplitude as E0I by eta, the direction being y, correct, and then you have e power minus jkz. So this is the incident magnetic field, right. Now there is also reflected magnetic field. Reflected magnetic field will be directed along minus y hat direction, right. It will have an amplitude of EOI by eta, correct. Only thing here is that now if the electric field is along minus x direction for the reflected field, right. So the reflected field is along minus x direction, propagation should happen along minus z direction, right. So what should be the component of H reflected? Well, you have minus x hat cross something must be along minus z hat. If H is along y, then this would be along minus x cross y, which would be along minus z direction, and therefore you can write this in this particular fashion. So you have reflected field as EOI by eta e power j k z, but EOI is actually minus EOR, therefore you have to write this thing as y hat EOI, sorry, I should have written this as EOR to begin with. You have y hat EOI by eta, right, e to the power minus jkz plus e power jkz, because EOR is minus EOI, right. So this would be the expression for the magnetic field phasor. Again, this e power minus jkz plus e power jkz can be written in terms of cos kz. So this becomes 2 times, right. So 2 times E0I by eta and cos kz. Again, this is an example of a standing wave, because you can actually write down the complete magnetic field H as a function of both z and t in region 1, and that would be equal to y hat 2 E0I divided by eta cos kz cos omega t, okay. So this is the expression for magnetic field. And what would be the situation for magnetic field at z is equal to 0? Will it be 0 or not? Well, it turns out that it need not be 0, right, because the condition for magnetic field is that the tangential continuity of H must be equal to the corresponding current density or the sheet current density that would be sustained on the conductor surface, right. So you have a conducting surface and there is a magnetic field, the tangential magnetic field. The discontinuity in the tangential magnetic fields will be equal to the sheet current density K, okay. And this is possible because you have a conductor, there will be current in that conductor that is induced, and that fact that H tangential 2 is 0 does not mean that H tangential 1 is also 0. In fact, H tangential 1 will actually be equal to current density or the sheet current density K. So you actually have the sheet current K along y direction having an actual value equal to, or the numerical value equal to 2 EOI by eta cos kz cos omega t. Of course, this must be evaluated at z equal to 0. So this would be 2 EOI divided by eta cos omega t. So there is actually a sinusoidal current sheet right on the conducting surface which would be non-zero, and in fact this current sheet would generate a magnetic field of its own, and then it would induce what is called as a radiation pressure on the conducting surface. We don't have to go into those details at this point, but just remember that boundary conditions indicate that tangential H continuity must be maintained, or discontinuity must be maintained by the sheet current density K, and in fact this is precisely what you are going to get. The magnetic field discontinuity will manifest in the form of sheet current density K, okay. So you can actually sketch at this particular point how would the fields look like away from the conductor. So this is my conductor surface that I have considered, and then if you look at the field, for the electric field, the field must be going to 0 at the origin or at the conducting surface. Therefore the electric field would go something like this with a maximum amplitude of 2 E0I, whereas the magnetic field would actually be non-zero at this point, and then it would go around like this, right. So I hope I am drawing them nicely. So it would actually go around like this with a maximum amplitude of 2 EOI by eta. What can you comment about the power carried by the wave? Well, the incident wave actually carries some power, right, because you have E cross H along the plus Z direction. E is EOI, H is EOI divided by eta. So the power that is carried by, or the Poynting vector that is incident associated with the incident wave, is given by EOI mod square divided by, and if you assume EOI to be real, then you can actually replace this magnitude square. So EOI square divided by eta. Okay, this would be the amplitude of the Poynting vector. What about the amplitude of the reflected vector? I have EOI minus eta, right, or minus EOI and minus EOI by eta is coming from the backward propagating, and the amplitude of that would also be EOI square by eta, except that this would be minus EOI by eta, except that this is minus Z propagating, this is plus Z propagating. The total power carried, the average power that is carried by the sum of the electric field and magnetic fields, or the waves in front of the conductor, will be equal to 0. So the average power carried will be equal to 0. Now how did I actually come up to this average power? Well, we have only seen one form of the Poynting vector, P is equal to E cross H, as the real Poynting vector, where electric field and magnetic fields were actually real, right. This is the real Poynting vector, and in fact this is the only type of vector that would exist. However, when you express electric field and magnetic field in terms of their phasors, then the Poynting vector expression can be simplified, right. With the help of phasors, if you write E as the corresponding phasor and H as the corresponding phasor, and for now let us consider them to be simple x directed and y directed phasors, okay, x and y directed phasors corresponding to a plane wave oscillating at a frequency e power j omega t and propagating along z axis, let us say, okay. So this is propagating along plus z direction, okay. Now for such a wave that I have, the Poynting vector P will be equal to some, with an amplitude of E0, it would be E0 in x direction, right, or if I go to the full Poynting vector, the real Poynting vector would be cos omega t minus kz, right, cross y hat E0 by eta cos omega t minus kz. So the Poynting vector P would actually be z directed with an amplitude of E0 square by eta, and then I have cos square omega t minus kz. Now if I ask what is the average power that is carried by this wave, to obtain the average power I have to integrate this one, right. So if I integrate this one over one time period, where omega into t is equal to 2 pi, right, where omega is 2 pi by t. So if I integrate this Poynting vector P with respect to time, I will see that integral of cos square omega t minus kz will give you half, right, and this fellow will become E0 square by 2 eta. Okay, so if I am looking at the average power that is carried by this, and then I am looking at the average power in terms of the magnitude, not really the vector. So you will see that this average power carried by a wave which is oscillating with a frequency omega and propagating along the plus z direction is given by E0 square by 2 eta. Okay. Now how can I obtain the same expression or same relation when electric field and magnetic fields are represented in terms of their phasor quantities? Well, in terms of the phasor, electric field will be Ex phasor, which is E0, this is still x hat up here, so E0 e power minus jkz, and the magnetic field phasor will be Hy, right, that would be along y, E0 by eta, this is not changed, e power minus jkz. Now what you form is, you form half of real part of E phasor times H phasor, right. So when you form this quantity, what you see here is half. Now not this E cross H phasor, what you actually form is E cross H complex conjugate. Okay, so you take H complex conjugate and then cross it with E and then take the real part. Well, if you substitute for electric field phasor and magnetic field phasor from these two expressions that I have given here, you will see that it would still be x cross y, that would be along the z axis, right, and then you have E field given by E0, H given by E0 by eta, therefore E0 square by eta will come out, and assuming that E0 is real, this entire thing will come out. Eta is also assumed to be real, so everything has come out, and what you am left inside is e power minus jkz into e to the power minus jkz's complex conjugate, which is e power plus jkz, right. So this fellow is equal to 1, and what I get is z hat E0 square by 2 eta. What is this quantity? This is half real part of E cross H complex conjugate, and this quantity is precisely equal to the average Poynting vector, right. This is exactly equal to the average Poynting vector, and you can actually, if you want to obtain the average Poynting vector and you have only the phasor relationships, you can actually obtain that. Okay. So this expression is very important, and if you look at this expression now in terms of what we have obtained for the electric and magnetic field of incident and reflected wave, you will then appreciate that the average Poynting vector will be with an amplitude of half here that I need to add. It would be EOI square by 2 eta carried along by the incident wave, EOI square by 2 eta carried along by the reflected wave. The sum of these two will actually turn out to be equal to 0. So there is no net average power carried by the total electric field in front of the conductor when there is a reflection. Okay. Well, we wrote down the reflection for a wave. Okay. However, in many cases we will be interested in finding out what is the ratio of the electric field that is reflected to the incident field, and what is the ratio of the magnetic field incident to the magnetic field. Okay. So this ratio of electric field reflected to electric field incident and ratio of electric field transmitted to the electric field incident define what is called as reflection coefficient and transmission coefficient. To really see that reflection and transmission coefficient, we need to move away from this normal incidence conducting type of surface to normal incidence dielectric kind of surfaces. Okay. So our next job would be to see what happens when you have reflection from dielectric interface. So if I look at reflection from a dielectric surface, what would that be? Okay. Assume that as before at z is equal to 0, there is one dielectric kept to the entire right hand side. So this dielectric is characterized by eta 2, this dielectric is characterized by eta 1. Now I am not characterizing them by mu and epsilon, right. I am actually characterizing them in terms of impedances eta 2 and eta 1, and let us now see what happens to the wave when it is incident normally. As before, let us assume that the wave is plane polarized, it is a uniform plane wave which is polarized along x direction and then travelling along the z direction. So this is the z direction and the wave is propagating along this, and then it meets, as initially it would be propagating in a medium of impedance eta 1, then it meets a medium of impedance eta 2, and let us see what really happens. Okay. First you have an incident wave. Because eta 1 and eta 2 are not the same, there will be some reflected wave. Okay. However, in this case now, because in a dielectric region you can actually have electric fields, there will be some electric field into the second medium, right. So because of this, at this interface you actually have incident, reflected and transmitted waves. So you have incident, you have reflected and you have transmitted waves into the second region. Accordingly, you have the reflection coefficient, which is the ratio of power reflected to power incident. You have transmission coefficient, or equivalently in terms of the electric field reflection coefficients also you can write, and then you have transmission coefficient in terms of transmitted electric field to incident electric field. The corresponding power functions are called as reflectance and transmittance. So these are reflection coefficient and transmission coefficient. Okay, how do I obtain this reflection coefficient, transmission coefficient? Well, it all boils down to writing the expressions and applying boundary conditions. Okay. Consider medium 1. Inside this medium, what is the total electric field? Well, it would be reflected field. So E in region 1 will be the sum of incident and reflected wave. What is incident wave? Let us assume that the amplitude of the incident wave is EOI. It is polarized along x direction and then it is propagating along z direction, right? Plus I have now the reflected field. Okay, reflected field will also be polarized along x. Okay, it cannot have a different polarization, and this is a fact that you will have to confirm yourself. And then the amplitude would be some EOR. At this point I do not know what is the relationship between EOR and EOI, right? So I am going to write this as EOR, but the wave is propagating along minus z direction, therefore I can write this as e power jkz. What would be the electric field in region 2? In region 2 I have electric field in the same polarization x, but this time it would be transmitted. So I have EOT e power minus jkz because the wave is propagating along z direction. Now what is the boundary condition that I can write? The boundary condition is that the total tangential electric field must be continuous across the boundary, right? Since x directed electric fields are tangential to the dielectric surface at z equal to 0, this condition at z equal to 0 boundary simply means that EOI plus EOR must be equal to EOT. I got one equation. Is that sufficient? Unfortunately no. I need to get one more equation. Where do I get that one? I can actually use magnetic fields, right? What is the magnetic field in region 1? Wave is directed along x direction, so I can write this as EOI by eta. This time it is along y direction, e power minus jkz, and then for the magnetic field, since we know that it has to propagate along minus z direction, let us reverse the direction of magnetic field. So this becomes minus y hat EOR by eta e to the power jkz, right? So that x directed reflected field cross minus y directed magnetic field will propagate in the minus z direction as I want. Okay. What is the magnetic field in region 2? Magnetic field in region 2 will be y hat EOT by eta 2, right? So I should actually clarify this one also as in the incident region as eta 1 and eta 1, and for this as eta 2. In medium 1 it is the ratio of electric field to magnetic field is eta 1, therefore this becomes EOI by eta 1, and the same thing for reflected field as well, it is EOR by eta 1, right? But in medium 2 it is the second medium impedance eta 2 that must be entered here, and then this will still be propagating along z direction. I have also assumed that there are no additional phase factors anywhere in this relationship. Okay. Now what is the condition for magnetic field? Well, the tangential magnetic fields, clearly this is still tangential to the z equal to 0 surface, must again be continuous now, right? There is no possibility of having any surface current as in the case of conductor, right? There is no possibility of having a surface current between dielectric to dielectric, because dielectric is assumed to be perfect and free of charges and currents. I have the boundary condition for magnetic field as tangential component H1 must be equal to tangential component H tan 2 and being continuous. So if this has to be continuous at z equal to 0, of course, what should be the expression for this continuity expression, that continuity equation, that the boundary condition, that would be EOI by eta 1 minus EOR by eta 1 must be equal to EOT by eta 2. Now I have all the required equations to go forward and calculate my reflection coefficient and transmission coefficient. How do I do that one? Let's suppose I take this eta 1 onto the right hand side, right, and then I am left with two equations, EOI plus EOR equals EOT, first equation, then EOI minus EOR is equal to eta 1 by eta 2 EOT. If I subtract, if I add these two equations, I get 2 EOI equals 1 plus eta 1 by eta 2 into EOT, right. Simplifying this, I get eta 2 plus eta 1 divided by eta 2, and the ratio of the transmitted electric field to the incident electric field, which we call as the transmission coefficient T. Some people use a small tau, small case tau, or use small letter t. All these are equivalent, don't really bother about which one it is. The point is that this transmission coefficient is the field transmission ratios, okay, that is, it is the ratio of electric field transmitted to incident electric field, and this is given by 2 eta 2 divided by eta 1 plus eta 2. Okay. What about the reflection coefficient? I can obtain the reflection coefficient from these two equations by subtracting 2 from 1. If I subtract 2 from 1, what do I get? I get 2 times EOR, right, because EOI gets subtracted out, must be equal to 1 minus eta 1 divided by eta 2 into EOT. This is nothing but eta 2 minus eta 1 divided by eta 2, right, EOR. 2 I can bring it down, but EOT I can write in terms of EOI, right. So EOT will be equal to 2 eta 2 divided by eta 1 plus eta 2 times EOI. 2 eta 2 in the numerator and denominator cancel, and I am left with ratio of EOR to EOI, which I will call as the reflection coefficient R. Some people use gamma as the reflection coefficient, or some people use small r as the reflection coefficient, doesn't really matter what you have used. So EOR by EOI is given by eta 2 minus eta 1 divided by eta 2 plus eta 1. Okay. So this is the ratio of electric field reflected to incident electric field, and this is the reflection coefficient. Now before leaving off this topic, let us also calculate the power transmission and power reflection coefficients. Okay. What do I mean by power transmission, power reflection coefficients? Well, what I mean is that what is the ratio of reflected power to incident power? This we call as the transmittivity. Maybe we can write this as T, okay, capital T or some slight script T, and similarly R as the reflectance, which is ratio, sorry, this has to be R, which is the reflectance, power reflected to power incident, and transmittivity or transmittance as power transmitted to power incident. Okay. What is the power reflected? Power reflected is the pointing power density that I am looking at. Okay. So if I consider a certain region of space, right, then power reflected can be written as directly proportional to pointing vector of the reflected field, right. What is the pointing vector of the reflected field? That would be EOR magnitude square divided by 2 eta 1 divided by incident power is EOI magnitude square divided by 2 eta 1. 2 eta 1 cancels with each other, and this is 2 eta 1 because they are in the same medium, and I get EOR by EOI magnitude square, which is nothing but reflectance or reflection coefficient magnitude square. Okay. So the reflectance is actually equal to reflection coefficient magnitude square. Okay. What about now the transmittance or the transmission power to incident power? Well, what would be the power transmitted? Power transmitted would be EOT magnitude square by 2 eta 2, because this is in the second medium, divided by incident power will be EOI magnitude square by 2 eta 1, right. So if you form this ratio, the transmittance is given by 2 cancels out, and then you have eta 1 onto the top. So you have eta 1 by eta 2 times EOT magnitude square by EOI square, which is nothing but transmission coefficient T. Okay. So this is the power reflection and power transmission coefficients. If the medium is lossless, right, if the medium is lossless, then what should happen? Then the total incident power must be conserved, right. So you cannot have any power loss which means that some power can be reflected, some power can be transmitted, but the sum of these reflected and transmitted powers must add up to the total input power. So the power incidence must be equal to power reflected plus power transmitted, right. So power reflected is actually written in terms of reflectance R times P incidence, and power transmitted is written in terms of the transmittance T or transmittivity T times power incident. Therefore, what this implies is that R reflectance plus transmittance must be equal to 1. Okay. Fortunately, this same kind of relationship, very similar kind of relationship actually holds even for the individual reflection coefficient and transmission coefficient, right. The expression should actually have been 2 eta 2 by eta 1 plus eta 2. So what is reflection coefficient R? R minus T. What would that be? That would be eta 2 minus eta 1 minus 2 eta 2 divided by eta 2 plus eta 1, right. And this eta 2 minus 2 eta 2 is nothing but minus eta 2 minus eta 1, or I can put the minus sign common, divided by eta 2 plus eta 1, that would be equal to minus 1, right. So now interchanging this minus T onto the left hand and the right hand side, what I have is 1 plus R is actually equal to T. Okay. From now on we will actually replace this R by gamma, standing for reflection coefficient, okay, and this T by tau standing for transmission coefficient. Okay. In many microwave circuits you are actually interested in this reflectance and transmittance, which actually tell you the ratio of power that is reflected to incident power and ratio of power transmitted to this one. And this reflectance or transmittance, and mostly reflectance you are interested, you actually measure this one not in linear scale but rather in decibel scale. That is, you actually take this reflectance and then form log of this reflectance. Okay. So when you do that one, you are expressing this reflectance in terms of dB, okay, and this is what you would obtain. So for example, if a certain microwave circuit, or if a certain wave, microwave circuit actually is reflecting the electromagnetic wave with a reflection coefficient gamma of say 0.9, right, this would mean reflectance R as magnitude gamma square, which is 0.9 square, right, which would be 0.81, okay, and then reflectance in dB will be equal to 10 log reflectance, right, reflectance will be 0.81. So whatever the value that you are going to get, you can actually write this one down, that is not really important. What I wanted to say was this 10 log, and you go back to the definition of the reflectance R, that would be magnitude gamma square, right. So this square, because of this square you can actually bring this 2 onto the left hand side, out of the log thing, and write this as 20 log magnitude of gamma. This would be the reflectance measured in terms of dB, and this is something that we will be using later when we discuss transmission line and then associated parameters, okay, and it is something that was also used in microwave circuits.